All right. My name is Eric Schwarz, and I love nuclear energy. Ever since I was 9 years old, in my dad's Scientific American Encyclopedia of Science and Technology, I was fascinated and enthralled by nuclear energy, and here I am, many years later, now getting to practice it every day. I have 27 years of experience in nuclear energy. I started out in the Navy as a submarine reactor operator, and then moved on to get my senior reactor operator license at the Penn State Reactor in State College while I was getting my undergraduate degree in chemistry. And then I went to graduate school for chemical engineering doing molten salt electrochemistry. So anything, if you've heard about advanced reactors and even waste burning reactor designs, molten salt is where it was at. I decided that I was going to enter commercial nuclear energy, and so then joined Peach Bottom Atomic Power Station in 2011 as the radiochemist. So my principal duties and responsibilities were related to measuring the amount of radiation that goes to the public, so all the radioactivity that's generated in the plant, and just understanding what that consequence is. I then worked at 3 Mile Island starting in 2015. Got my pressurized water reactor senior reactor operator certification there on their systems, and worked in the nuclear steam supply systems group up until 2019. And then when the plant closed in 2019, I returned to Peach Bottom as a reactor safety systems engineer there, and worked there until July 23, where I took an instructor role. So you'll see me sometimes act more instructor-like than open lecture, and then I recently took a position at 3 Mile Island again for the restart. So I'm the lead chemical engineer there for the radioactive waste systems. Okay. So why is this talk relevant today? We'll get into that. You are surrounded, if you're in Lancaster, by 3 nuclear power plants, and that is uncommon. There are not too many places you can be that makes that true. And before we get started, everything that I say tonight has nothing to do with my employer, Constellation Energy, so all opinions provided today are my own. They also do not express the opinions of Franklin Marshall College. I'm a senior research associate there for radiochemistry in their group. So some things I'll talk about for radiation in the environment may coincide with that. So I want to start off with just talking about some concepts of nuclear safety, and from my very early training, we learned about the principles of design. And one thing that stuck out always is that no single failure can cause or prevent a safety system actuation. And when you think about what that means, it means that human beings really become the problem when we start operating nuclear reactors. The accident at 3 Mile Island, for example, represented a situation where if they were just hands-off on the controls, all the systems would have functioned well, with the exception of the emergency feed water, which was still to this day unknown why all 4 isolation valves were found closed. But had they had emergency feed water fire off, they would have also been able to save the day there too. But even that situation was not going to damage the core. No, it was the human beings that kind of made it further complicated. So when we design our systems, we make sure that we look at those single failure points when we design for that. We have this concept too called the 3 barrier criteria. So the big thing with fission products is that they're supposed to stay in the fuel and not leave. And the best way we can do that is making sure that the cladding on the fuel, that is, if you can kind of envision each of the fuel rods themselves, is this thin stainless steel sheath that covers each of the fuel elements, or fuel pellets. And then all of that sits within the reactor coolant system. So this reactor coolant system now is this boundary where a lot of the heat transfer occurs, but also it's where we also want all the fission products to maintain if there's a failure in that cladding. And then beyond that is the primary containment system. So that prevents the fission products from entering in the atmosphere and then dosing the public. Peach Bottom's safety analysis report also talks about a secondary containment, which is not really credited for safety systems, but it's still there to help out a little bit. And then finally, the the other core, no pun intended, I guess, core concept of nuclear safety is keeping the core covered and keeping the core cooled. So what this means is that liquid water is a much better coolant than steam is, and at the point where you cannot put liquid water on the core, you are in deep trouble. So if you can keep your head in the game at any nuclear reactor, this is all that matters. And dumping water from any source always saves the day. And that is how we trained in the Navy. Here's an example of a image from 3 Mile Island Unit 2 accident, which is not a BWR, but it's at least instructive. Maybe you've seen this already online. This is a fairly common, this is very famous from after the accident. But what it shows is the amount of core damage was extensive. About 2/3 of the core relocated to the bottom of the vessel. And this was because, like I said, the operators kept trying their best to screw it up throughout the accident. And one of the things they did was they interrupted cooling and then they restarted the reactor coolant pumps thinking that they wanted to save them for later on, and that was the wrong choice. This caused a steam bubble to form here, and as I mentioned earlier, steam is a very poor conductor of heat, and so this steam bubble is really what damaged the fuel beyond the 220-degree Fahrenheit limit. So shattered like glass once they restarted the pumps and put a slug of cold water back in the core. These are principles, again, like I said, that every young reactor operator on submarines is taught, and I think that they're just kind of good to know. So the boiling water reactors, like I mentioned, are a different design. Maybe, you know, 3 Mile Island was known as a pressurized water reactor. A boiling water reactor is one that boils in the core. And why you would want to do that, right? Why is that important? I just mentioned how steam is a very poor conductor of heat. And that's right, but steam is also great because the amount of energy that steam has works well in a steam engine system that we would, you know, we want to make useful work out of it, right? So we use the steam to expand into a turbine, and that turbine turns, making electricity. And then I can just take that liquid water back into the core and inject it, and then now I can complete the steam cycle over and over again, which is very useful. We get a small amount of energy efficiency out of the boiling water reactor design than we do the pressurized water reactor. So this does have an obvious engineering advantage. The disadvantage, though, is that the steam is all radioactive, and so I can't access any of these steam systems at power. And when I'm shut down, I have to have contamination controls in place in order to work with it. But I like boiling water reactors. They are very interesting. So the difference between these two designs, as you can see, this is more the peach bottom design. It's got the characteristic hourglass shape of the BWR 4 from General Electric. And then this is more the Limerick design. So this is peach bottom up top, 2 units, Unit 2 and Unit 3. And then units 1 and 2 here at Limerick, shown here. And Limerick's also got this characteristic spray pond here. This is part of their emergency core cooling system that they use to cool this thing right here, which is called the suppression pool. And the suppression pool, we'll see in a minute why that is important. So the BWR-4 from General Electric was very interesting. It's probably one of the most popular designs by General Electric. There is a BWR-5 and a 6. Currently still in operation around the world, and they are fantastic, much better designs in terms of like a lot of the safety systems. But like I said, this is still very popular. Peach Bottom Unit 2 and 3 looks almost identical to this layout, as does Fukushima Units 3 and 4, which is, of course, famous by the Fukushima Daiichi event that happened in, March 13th, 2011. Yes, sir? Oh, yeah. So Chernobyl is interesting. Those reactors were designed to be as cheap as possible to generate electricity, but as well as fuel for, generate plutonium for weapons production as well. So you could do it all at a very low cost. And when you do that, yes. It does. It does. It's a major trade-off. And in fact, they used aluminum cladding on a lot of key reactor safety systems boundaries, and aluminum had a much lower melting point than did the fuel, and that is also bad. So as long as you operate I mean, the RBMK design is okay as long as you don't go outside your safety envelope. But once you do that, now, you know, what is it? You know, there's no salvation beyond this threshold that you enter. So we also train like that too, where we have more safety margins here in these designs than Chernobyl did, but we treat it like it is our last barrier. So thank you for the question. Anyone else can interrupt me as well, so don't think, you know, you have to wait till I'm done talking. So, this talk is really now about the emergency core cooling systems and the strategy to combat the design basis accident. And so very broadly, and again, this is kind of training that you would get at a nuclear power plant, and I'm compressing it in a very short period of time, but I think it'll give you a pretty good overview of what's at stake in terms of layers of safety. So we've got various systems that are relied upon in order to add cooling to the core. And the concept that I said earlier about no single failure can cause or prevent a safety actuation is true here, because what I use is a concept of the diverse and independent methods of getting coolant into the core. Some of these pumps are steam driven, some of them are electric driven, and if they're electric driven, they're driven from different sources, so that any one failure of a source doesn't knock out all my capability of doing any cooling. I first have the high pressure coolant injection. We call it HIPSI. It has a sister pump called RICSI, Reactor Core Isolation Cooling Pump. And we've got, and as the name implies, right, this only injects coolant at high pressure. And then we have core spray pumps. So here we show 2 core spray pumps. Peach Bottom actually has 4 core spray pumps. And these, as the name implies, sprays the core. So you can see the injection line here from the pumps go inside the shroud, and there's 2 rings that encircle the fuel right at the top that are meant to spray down into the fuel as your last ditch effort, we'll say, to remove a significant amount of heat. As you remember, you know, atomized water, liquid water droplets, they flash to steam very quickly, but they'll also remove a lot of heat very rapidly. But hopefully, we don't have to rely on core spray systems. And next we have the low pressure coolant injection we call LIPSI, and it is a 2-train system, but each comprises of themselves 2 independent trains. We draw 1 heat exchanger here, but Peach Bottom actually has 2 heat exchangers per loop. And the great thing is, too, is that we just completed a modification maybe like 8 years ago to cross-connect those safety systems so that actually I have a lot more flexibility. And if any one failure of a heat exchanger or a pump during an accident, I can swap over to the other one. So I get a lot more bang for my buck now in terms of reactor safety. And then you'll notice here I have this one called ADS-equipped SRVs. And this is the automatic depressurization. Yes, sir. Tim. No, we will come to that in a second. You'll see that for the worst case scenario, that is our first line of defense for keeping the core covered, but thank you. So the ADS SRVs right here, this is the automatic depressurization system, so I can enter what we call blowdown to the plant as soon as we have a situation where I need to get a lot of water into the core rapidly. I can open those valves manually, or the safety systems will actuate themselves, allowing it to blow down, and then I can add water elsewhere. So these low-pressure coolant injection systems, they don't work if I'm at too high a pressure. They are only designed to remove decay heat at low pressure. So, and that is, oh, and here's the suppression pool. So you saw that the donut right here, like a Peach Bottom has, that's shown here, just a slice here, and it's filled with more than 1 million gallons of water, and it's used as our safety-related injection source of water. So If we're going to operate normally, green means off or closed for these valves. Red means open or on. And normally, none of these safety systems are functioning. We have liquid water being recirculated through the core, boiling off, and then that steam is carried off to make a lot of money. But on a bad day, we have what's known as the worst case scenario, which is the small break loss of coolant accident. So for Peach Bottom, this is defined as the suction side of one of the recirc pumps completely shears off. And this will cause immediately not only a lot of liquid water to come out, but it's going to flash to steam because it's at 540 Fahrenheit and over 1,000 pounds. But it'll quickly depressurize in the containment here, the light bulb, to be over 2 pounds. And at that point in time, our safety systems will fire off. And now, as you can imagine, the pressure inside this dry well, the containment, will now rise. Reactor protection system actuates, and we'll get the diesels, the emergency diesels, to start and run, anticipating a loss of the grid. Because right now, if we lost power and we had no other way to power some of these other pumps, we would be in real trouble. And that is unfortunately what happened at Fukushima Daiichi. They were unable to utilize their emergency diesels because their diesel fuel oil tank was not buried. It floated away on the tsunami waves. We do not build that like that here in the United States, so that is not a concern of ours. And Tim, just like I had said earlier, high pressure coolant injection begins, and that's at 9,000 GPM. So right now, it's actually going to be a steam-driven pump. These valves right here, this motor-operated valve, and this motor-operated valve, and this motor-operated valve, all reposition because they're open on de-energization. And then that puts the steam to the turbine drive on that HPSI pump, and then we're pushing a whole lot of water into the core right now. In fact, it's going to go on the outside, push its way down the downcomer, and then maintain coolant level here. But I can't do this forever because this is not a cooling method. I don't actually have a heat exchanger associated with this, right? And then the accident water that's coming out of the plant, it's all flowing down now to refill into the safety-related source, which is the torus, which is then being picked back up at the suction HPSI to be circulated through. As you can imagine, this can't be done forever. I have to do something with this. Plus, as the system begins to lose energy inside of it, the steam pressure is going to go down more and more, so eventually HPSI is not going to work any longer. Operators do not have to do anything, but stand back and let the system take care of itself, but they won't stand back and do it. But if they did stand back and not do anything, not touch anything, then the ADS inhibit signal will be set to false as normally. So this means that the automatic safety systems will now open all the ADS valves, which is five on Peach Bottom units 2 and 3, and then this will depressurize the system. It's a saturated system thermodynamically, so if you remember anything from physics class or whatever, this means that pressure and temperature follow each other. So if I lower pressure, I can lower temperature in the plant, and if I lower temperature, I can lower pressure in the plant. And this works beautifully, synergistically, to help us provide some cooling now by blowing all this steam. It's going into the torus, right? The steam has, you can see little downcomer regions here, where it's now going to condense, creates a vacuum, lowers pressure in containment while we're trying to get the system down to where LPSI, the low pressure coolant injection system, can inject. HPSI will be secured because we're now below 200 pounds in steam pressure, so I can't use it any longer. And that's okay because now I have this super redundant, very reliable RHR system, also known as a residual heat removal system, where I can push all the water in these heat exchangers. These are cooled by the Susquehanna River themselves, so I can reject almost infinitely amount of heat for many, many days. In fact, our cooling system is designed for safety-related mission time is 7 days, which is way longer than you need, but you never know what happens. So, all right. So, why do we need to have so much cooling for nuclear reactors, especially when they shut down, right? Once you scram, once you turn it off, what's the problem? Well, there's this concept called decay heat, which makes nuclear energy special and unique, right? The fission products don't all stop making heat just because you shut the reactor down. If I had a gas plant and I shut it down, yeah, the metal's going to be hot for a while and I can put some water through it and it'll cool down pretty rapidly if I needed to. But not nuclear fuel. Because unfortunately, or fortunately, depending on your perspective, because if you want to start right back up, it's actually a net gain. But if you want to shut down and keep the core cooled, you have to manage a whole lot of heat. In fact, it's 7% of your core operating history at the point of shutdown. So if I'm operating at 4,000 megawatts, which is the rated core power for units 2 and 3 at Peach Bottom, 7% of that's 280 megawatts I have to deal with immediately upon shutdown, which is a very large amount of power. And enough to melt the fuel if I can't remove that heat rapidly enough. And that's because all the fission fragments in there, they all are positively charged, they move, right? They impart kinetic energy to the fuel as they decay, and they don't all do it at the same time. They are radioactive themselves, and their half-lives take place over some of them very short time scales in order of microseconds, minutes. Some of them very long time scales in terms of hours and days. So we have to manage that heat. So that's all that I have. Thank you very much for the opportunity to come shoot you with a fire hose of knowledge on a topic that I traditionally have done just professionally. So thank you.
How should we feel about Microsoft wanting to manage our 3 Mile Island?
Well, again, I don't speak for Constellation, but I think it's a pretty good deal. I mean, we get to do something we've never done before in the history of the world. We get to restart a decommissioned nuclear reactor. We are going to learn a lot of things. I'm very humbled to be part of this project myself, and it's tough because as I was describing to Steve earlier, is that it's not just undoing all the things that we did, it's now actually forging a new path for how we're going to restore the systems, now certainly financially, but also making sure that we're not, we're cleaning certain systems up in a sequence that makes sense. So I could give a talk on what we did to decommission 3 Mile Island, and then when we got the turnaround signal, what that chaos kind of looked like. Because as you imagine, when the news releases came out, there were a lot of people who were very surprised at what wasn't happening within the company at that time. And it was very interesting how things are now evolving, because we're not a construction company. Constellation has no experience with constructing new nuclear reactors. We are bringing in a lot of outside help for that. So yeah, it's again, I think it's great. Microsoft wants to give us a ton of money to operate, because it's a ton. Yes, sir.
Yeah, I saw a little video on how they're restarting up, one of the reactors, and it looked to me, and maybe you could correct it, they're reusing a lot of the stuff that was there, and some of it, to my eyes, looks fairly ancient, like the controls, things like that. How do you feel about that?
Yeah, everything you just said was 100% accurate. So we are starting, I'll just be honest with you, we are starting to have internal conversations about, does it really make sense to refurbish the old stuff?
I mean, it looked old.
Yes.
I mean,
yeah. So the original plan, like I said, was we're just going to turn it all around, close the breakers, bring everything back up and running, and we'll be good to go. We'll just do some maintenance, and and it's not like that. It won't be like that. There's panels that haven't been turned off since 1968, and then they were turned off in 2019, and it was like, well, we'll never use this again, so who cares? and when we anticipated shutting down, right, we even stopped doing maintenance on certain things because why, right? So I think that's becoming a bigger reality that we have to face. So there has been talk about digitization of certain old analog systems, but that scope is like merely a twinkle in somebody's eye at the moment. There's a ton of money that's being available. Like we're spending, well, I won't give you the dollar figure, but it's a very large number. Whatever number you can think of, then double that. That's how much we're spending just to put Wi-Fi in the plant. I never knew that IT could be that expensive, but it sure is.
And is this plant only going to be for the data center, or is it going to go into the electrical grid?
So, yes, what a great question. I have heard a lot of things, and one of them is that all we are being paid to do is provide this power from this plant. Now, what does, yeah, we really don't know. Or they're keeping that a great secret. I don't know. But all I know is that this money is to bring back 3 Mile Island for the sole purpose of having clean power for Microsoft's data center. That is the message. So yeah, appreciate it. Yes, sir.
So with all the safety systems being like the way you described, what type of manual human input is required for that? Is it just to switch the systems from high pressure to low pressure, or are they just there to monitor what's going on when stuff is going on?
If the entire control room staff was incapacitated and could not do anything, all the systems are designed to function automatically. Human beings are really there at that point and are trained to look at their indications, make sure that if this pump indicates that it lit off, well, then that means that I should be seeing water moving in the direction I need it to, right? So everything's a series of checks. There are situations, we run scenarios all the time where equipment doesn't function, and now what are we going to do? So there are alternate paths. I gave you like the very vanilla scenario, like how it's supposed to go. There are scenarios where none of those pumps are available. And so now what do you do? And it's interesting. It's very interesting stuff. But yeah, good question. Ken?
So speaking about the testing and validation,
Yes.
all those systems can test it independently without putting the reactor out. So you can test the pressure building up, setting up the valves, everything else.
Yes, we can test a lot of stuff. We will, because we can't raise pressure to actually test those detectors in service, we'll remove them and then do bench testing on them, and then, but everything else, the logic systems can be tested independently of that.
They won't test what the reactor is running to make sure the systems are still.
Oh yes, and a lot of them are mandated by the regulator as well. So we have quarterly in-service testing is what they call that. So we actually have to start and run a lot of these pumps too to make sure they have the design, flow, and pressure. So we'll divert the flow to go someplace else that doesn't go into the core, but yeah, but they get tested. Yes, sir.
Yeah, back to the topic of clean energy. Many opponents of nuclear talk about solar fusion.
Yes. When you look at the sheer volume of nuclear waste, it's not really that much. And compared to other energy sources, it's a solid form that can be dealt with, unlike, for example, natural gas, which is a gas, or any other carbon-emitting source. I look at it, from an engineering perspective, and I find that dealing with nuclear waste is far easier when you can start partitioning and separating out certain bits, because like I said, some of the fission products, they have much longer half-lives than others, right? So that means that I can actually deal with them in different ways. If I understand the chemistry, I can deal with them differently. And then of course there are reactors that were designed in the 1950s that have been tested that burn nuclear waste themselves. So it's really a technological problem that has been solved, and it's more now of a political problem to kind of get you in that particular direction. And I'll just say too that the Canadian government is right now investing a lot of money in a waste-burning style reactor that is very interesting, because they could buy, for example, our waste in the United States for $1, and then they just burn it and make essentially very cheap energy with their molten salt waste burner. So I'm looking forward to it. I think it's at the Point Lepreau station in Nova Scotia where they're planning on building that pilot plant. So yeah, I personally think that a lot of nuclear waste fears are overblown. Even the transportation of the waste, that's usually the big boogeyman. Those casks are extensively tested to withstand a lot of events. So yeah. Yes, sir.
I'm just curious, what's the capacity of the heat exchanger? Does that handle a full operating reactor just dumping all of that heat?
Nah.
Or is that just the decay?
Well, no, it cannot handle it cannot handle all 4,000 megawatts. That is an enormous amount of power. So you do have to get it down to a particular manageable level. I left out a few details, right? Like I can dump steam, which is enormous. If I have the grid suddenly reject me because maybe my generator trips offline, or we get a major blackout, which happened in August 2003, the turbine will trip, but the reactor had already sent all this energy, and it's got to go somewhere. So we can dump about 26% to the main condenser, but that is also problematic. So the safety relief valves also act as safeties for the system and will dump the rest of the energy into that torus where it can be absorbed. And then, like I said earlier, so now I've transferred a whole lot of that energy down. Not only that, but reactor begins to depressurize quite a bit, so the reactor cools quite a bit, and now the operating staff has to just kind of manage that cool down by bleeding steam until they get to a point where they can bring on LIPSI. So, yeah. Good question. Good question. Integrated plant. Yes, sir. I did. Yeah. Yeah, it was fantastic. It's funny. They told me at boot camp you get more money if you go on subs. I was like, all right. I actually had no idea what I was getting into. So I think it was awesome. Like the things that I saw from a submarine perspective, from a surface ship, because I actually visited surface ships, saw what they had to deal with. I'm glad I made the choice that way. So because for me, most people I meet, like some of the other surface Navy guys, they couldn't stand the idea of being on a submarine. So yeah.
Got over your claustrophobia real quick.
I didn't have claustrophobia. I get more claustrophobia on an airplane, to be honest. Yes, sir.
Are there threats that were not needed to be considered before that need to be considered out?
Yes. Following the terrorist attacks on September 11th, NRC had a confirmatory action order to all licensees that they had to have what is ominously known as B5B controls, which is a particular regulatory line item, B5B. And it's the NRC asks you to take certain actions to have stuff in place so that you can keep the spent fuel pool cooled and covered, but the specific threat is not named in there. So it's just additional augmented actions that you had to do for other things too. So yeah, it's been an interesting ride with that, but there's other things now with drones and attacking infrastructure. So yeah, that's all ongoing. That's very interesting stuff. So yes, sir.
So you kind of answered this probably a little bit earlier. You mentioned a lot of stuff is older, and you talked about digitization.
Mm-hmm.
Has there been a ton of technological change? A lot of your technologists, there's new JavaScript framework every week or whatever. So it's like there's a ton of change in the nuclear reactor space. Has there been a lot of change from when 3 Mile Island was built till now, or is running the old stuff still like this is still pretty good technology?
Yeah, the best part about a lot of this technology is it is cyber secure, right? There are so many things I could describe to you and show you, but I mean, as you can imagine, all this analog stuff, like a lot of it's analog computers built in the mid-1960s that worked beautifully. Well, they worked beautifully, before the place shut down, and it actually was unique because no other nuclear plant had such a system that would control everything from the control rods to the turbine. And with a single potentiometer swipe, I can make the whole plant ramp up and down. And everything kind of sings together like at a beautiful choir. Like it was unbelievable. And it was very robust too. Like it had very few problems. And now we don't believe that that's true. $40,000 a piece to refurbish each one of those modules, and we have hundreds of them. And that was the big impetus, honestly. And as you can imagine, that's just but one system on one plant. Consider now Constellation owns, 13 reactor sites and a bunch of reactors, right? So like 20-something, 24 reactors. Well, more than that now, but it's like 26 reactors. So we were spending a lot of money to refurbish all the old cards and systems built by GE from the 70s and the 80s. Like their Z80 chip is used extensively. And oh yeah, if you're a big programmer, GE's got a ton of money for you to come work for them because they still manage these contracts today. Like it's all safety related stuff. So in order for me to do an engineering change to any of this stuff, to do something new, I have to spend at least $2 million to just get somebody in the door to come tell me like what the best options are, right? So Limerick is undergoing the nation's first digital instrumentation and control system for reactor protection right now. That project is encountering a lot of hiccups. It's progressing, but it is one of those like just growing pains of the industry. So we are probably a few decades behind, because I'm going to tell you this, when I was in the Navy, we had technology from the 1980s, like they were all like 8080 processors in our reactor protection systems and everything, all our nuclear instrumentation, and all these modules were like this big. You go to like Peach Bottom, they're just giant cabinets for each one of those functions, same functions and everything. And they were all digital, 100% digital, because the Navy saw like what an awesome thing this is to now shrink all that stuff down into, tiny units, because space is a premium on a submarine. So, but yeah, then you go to commercial and you go like, well, how come we don't have anything like that? It's like, well, because the Navy has an unlimited pot of money to spend on all this stuff. Yes, sir. Well, no. So the government does not have to review everything, but and the Nuclear Regulatory Commission would be our final reviewer. But we do have a process that allows us to make changes to our own plants using our own processes that we have, unless you make a change to a function as described in your safety analysis report. Then it may need to go to the government for review. So it's only and those are very, very few and far between, right? Unless we see a real economic advantage for doing that, we will not change a function as described in our license basis already. So,
Last question.
Yes, sir.
I was gonna say, when was the last time you used the power plant was built in the US?
The 80s? Well, so Vogtle 3 and 4 were the last two plants built and completed, and that was way over budget and way over schedule. So they just started up and went on the grid like a couple years ago. So yeah. Thank you.
Thank you very much.